Okay, it's Mr. Benson here with a video on factorising, which is our next area that we need to look at. So factors, we've got to think about what they are. So factors are numbers which multiply together to give a particular product. So for example, factors of 12 are 3 and 4. So 3 times 4 equals 12. So 3 and 4 in this case are factors. Now what we've got to remember is that there are often lots of different factors of a number. So if we think about 21, what are the factors of 21? Well, you can have 1 times 21, and the other one you can have is 3 times 7 in this case. Okay, now another idea is highest common factors for what we're going to think about. So if we think about numbers, these two numbers here, so 48, so what are factors of these ones? Well, 48, well obviously we've got 1 and 48, we've got 2 and 24, what else have we got? We've got 3 times 16, 4 times 12, 48's got a lot of factors, 6 times 8, okay, and I think that's all. Okay, 30, 1 times 30, 2 times 15, 3 times 10, and we can do 6 times 5. Okay, so what are the highest common factors of these two numbers? Now you look through these two lists, assuming I haven't missed anything, and we see that 6 is the highest common factor of both these two numbers, and that's an idea that's going to become important later on. Okay, so factorising expressions. Now we know that we can break numbers into factors, as we've seen just in the previous slide. Now we can factorise expressions as well, and what we've got to do is think about the terms in the expression and what are the highest common factors of those two terms. So if we think about this term here, so we've got 2x, and this term here we've got 6y. Now what we can think about here is that 6 is a multiple of 2, so remember that 6 is 2 times 3. So we've got a common factor of 2 in both these terms of the expression. So we can take that out. So we take out that factor, and then in brackets we leave everything that's left behind if we were to divide this expression by 2. So 2x divided by 2, all we're left with is x, and then 6y divided by 2, all we're left with is 3y. Now we can check that we've done the right thing here by expanding, which we've just spent a whole lot of time doing. So if I was to expand back the other way, so 2 times x is 2x, 2 times 3y is 6y. Okay, a couple more examples. Now what you might like to do is to have a go at these yourself and then let me then watch my solution to them. So with the first one, now pause if you want to have a go at that. Now the factors, there's a couple of things we've got to think about here. So 3 is a factor of both terms, so I'm going to write that down first. But we've also got a as a factor of both terms. So I'm going to write 3a on the outside. Now if we divided this first term by 3a, well the 3 is going to cancel, and the a squared all we'd be left with is a. Now with the second term, if we divided that by 3, or 3a rather, all we'd be left with is 3. Okay, moving on to the second one. Now again, pause this if you'd like to have a go yourself. So when I look at this, there are a couple of things I can see. Both of the terms contain y. Both of them start with a negative sign, so I can write a negative sign there. Now both of these are divisible by 2, so I can put 2 as a factor. So when I look at what's left, if I was to divide negative 4y squared by minus 2, well the number I'm going to be left with is plus 2, and y squared divided by y is y. Now over here, if I divide negative 2y by negative 2y, I've got plus 1. So those are my two factors. Now we often want to do some harder factorization with binomial factors. Now remember from what we were just doing with our expansion that we can multiply binomial factors, so this is the sort of standard expanding that we've been doing with a single bracket, and we can also do the more complex expansion with double brackets and also our expansion patterns that we've just been looking at. So if we can multiply things by binomial factors to get a product, then it makes sense that we can factorize expressions to get the binomial factors. Okay, so one thing that we can look at is the highest common binomial factor. And this is usually when you have expressions that are written in this form. Sometimes you're able to go another step in the process from a fully expanded expression and then break it down to its binomial factors, but that's probably getting a bit ahead. Okay, so with this expression here, what we can see is that we've got the same binomial factor in both terms. So we can take that out. Now, it's really no different to what we were doing before, except what we're taking out as a factor is a binomial. Then what's going to be left in the brackets is everything that remains once we've divided by this factor. So if we were dividing this first term here by x plus 3, then the x plus 3 would cancel and all we'd be left with is x. With the second term, if we were taking out the x plus 3 by division, all we're going to be left with is minus 5. So we've factorized this expression by taking out the binomial factor, and then we end up with a second binomial term here. Another approach that we can sometimes do is factorize by grouping terms. Now, this is usually useful when you've got more than one different pronumeral in your expression. Now, when you're doing terms that just have, say, x as your pronumeral, and you might have x squared and x in there, this is not always as useful. Now, it doesn't really matter how you do this because it's probably going to work out much the same in the end. All you've got to do is group your terms so they've got some common factors, and then see what happens when you factorize them. So what I mean by that is, let's look at these ones which have a common factor of 5, and we'll look at these ones over here which have a common factor of c. So let's factorize these individually and see what happens. So thinking about our first one, a common factor of 5, so I'll write that outside the brackets. Now what's left? Well, a for the first term, then dividing the second term by 5, we've got 2b. Okay, cool. Then with the next term, or terms, we've got a common factor of c, so I'm going to take that out. Now with the first term here, if I divide that by c, all I'm left with is a. With the second term here, if I divide that by c, all I'm left with is 2b. Now, what you might have noticed here is we've gone from this expression up here, which has a whole bunch of different terms in it, to now a situation where you have a common binomial factor. So I can go one step further now. I can take out that binomial factor, as you saw previously, and we end up with two binomial factors like this. Now, there's a couple of things that you might remember as well, and you might find useful, although this is getting a little bit further ahead. If you remember your expansion patterns, you can also work backwards from those to factorize, and you don't really need to do a lot of calculation when you're doing this. So if we think about perfect squares, so x squared plus 2x plus 1, now that is the product of two identical binomials, and in this case it is x plus 1 times x plus 1. Now the pattern you might remember from perfect squares is that it is, so say we had x plus a squared, it's going to be x squared plus 2ax plus a squared. And so in this case, so 2 times 1, so 2a is 2, and 1 squared up here is just 1. So if you ever see something that follows this kind of pattern, you can probably factorize that into a perfect square. Just to make up another example, so let's go with, say, x squared minus 6x plus 9. Well, looking at this, I can see that this is the same as x squared plus 2 times minus 3 x plus, now 9 is also minus 3 squared, so this must be the same as x minus 3 squared. I know these might not seem obvious, and that's okay. This is definitely getting into slightly harder stuff, but by remembering our expansion patterns, we can work backwards to factorize. So difference of two squares is the same thing. X squared minus 9, now these are both perfect squares, so x squared and 9 are both perfect squares. So this is maybe a little bit more obvious than the previous ones up here with perfect squares, is that when we've got the difference of just two squares, this pattern's really distinctive. Now what that means is it's got to be, in this case, x minus 3 x plus 3. And say if we had another one, I don't know, x squared minus 25, then that's got to be x minus 5 and x plus 5 as the two factors. So that's slightly more advanced factorization, but it's pretty easy to remember if you can remember your expansion patterns.